Hello everyone, welcome back to Diksha Karnataka YouTube channel, and today in the Decode NCERT series I am going to discuss the chapter Dual Nature of Radiation and Matter, a very important chapter in terms of competitive exam, in terms of scoring opportunity in your board exam as well. And as usual, if you are following this series, you know that you have to open your book and I am help you to understand from where you have to read, which parts are important, which formulas are important, which from where you will get the questions from. So this is the exercise that you already are aware of. So let's start without any delay about this chapter, Dual Nature of Radiation and Matter. Now in the introduction part, there is nothing much there. You can just read about some history, how the discovery started, what is the ratio of mass, charge to mass ratio of electron, etc. Okay. Nothing super is important there. The first important concept from this chapter is the conversion of electron volt into joules. So 1 electron volt is basically 1.6 into 10 to the power of minus 19 joules, which is nothing but the charge of an electron. So we now know that electron volt is basically a unit of energy, a special unit of energy, and it can be converted into joules by using this factor 1.6 into 10 to the power of minus 19. So these are the points that you have to remember, especially if you want to convert units from electron volt to joules to electron volt. We have seen in nuclear chapter that we whenever we are considering energies in a nuclear level, we generally consider mega electron volt. Okay, so mega electron volt is basically 10 to the power 6 electron volt, right? Because energies of a single electron is very small. So if we represent it using joules, that will be very incorrect. But in if you consider in electron volt with respect to two different electrons, that is when you comparing two electrons, that is very high, right? So that is why electron volt is a common unit, and it is basically defined by the energy possessed by an electron when it is accelerating in 1 volt 1 volt potential difference. Okay, now let us move into the different types of thermoionic emission. Okay, emission of electrons. We know that metals consist of metals consist of free electrons. Now everyone was trying to harness those electrons to make them obey their commands. Okay, so the people were trying, there are different ways to do that. First is thermoionic emission. Thermoionic emission is very simple. You heat metal, okay, the metal will emit some electrons. Okay, this is very common and simple process. Okay, and there are some methods, some process where it is used in the very early days of electronics. Okay, there was a thermoionic emission there. They used to control those electrons using potentials. So those are the days when heating effect was very common. Now, but that is required heat, and if you want to use heat, nowadays we are trying to reduce the heat developed in our devices. So it is very difficult to control that heat, right? So if you are heating itself to make the things operate, then it will again heat the machine, and it will create some problems. So next stage was field emission. Field emission is when you apply a very high electric field, and we know that electron moves in the opposite direction of electric field. So applying high electric field between metal plates, one metal will emit some electron towards the other metal. Basically it is a contactless emission, right? Contactless flow of electrons. That is very important. Electrons are always flowing in a conductor, but contactless flow is somewhat important in many cases. So one such example of field emission is Jenner diode. Jenner diode is no longer part of your syllabus, and the explanation detailed here is obviously not part of your syllabus, but you should know that Jenner diode, where electrons are pulled out from one part to another by using high electric field. Now most interesting and intriguing of all the three is photoelectric effect. When you light show light on some metals, the metals tend to emit electrons, which is very, very interesting, because we know that heating effect can give you electron, because electron is gaining energy, and that energy is basically released, the energy giving the electron to release the metal. But how can light give something to emit electron, which is very, very interesting at that point of time. And many people thought it may be an extension of heating effect, thermoionic emission, where you are basically electron is getting heated because of the light. But there are some observations which negated those explanations, and only when Einstein came up with a completely new explanation at that point of time, it was able to explain the entire phenomena. Okay, and that gives rise to a new science, quantum physics. Okay, Planck is even Planck was there before Einstein in terms of heat, but anyway, this was the starting point of a new physics, quantum mechanics, quantum physics. So this is a starting point. This is the very, very important thing. It is the stepping stone of this quantum mechanics. That's why this chapter is part of your syllabus right now. The first two persons who started their experiment on photoelectric effect was Hallwach and Leonard. So Hallwach and Leonard, they started their experiment, and they did a lot of experimentation with photoelectric emissions. Okay, so what they have discovered is that negatively charged particles were emitted from the zinc plate under the action of ultraviolet light. So what they have done, they have taken an zinc plate and they shine ultraviolet light on the zinc plate, and then they observed that negatively charged particle was coming. And this is I think even before the discovery of electron, I think 1800 something. The experimentation was very old, they are not super new. Okay, 1886 and 1902, during that time they are doing this. Almost 124 to 130 years ago they were doing this kind of experiments. And we know that in 1997 J.J. Thomson discovered electrons. So they now realize that whatever is coming out of that surface is basically electrons. Okay, and then they realize that no electrons are emitted at all when the frequency of the incident light was smaller than a certain minimum value. So that is very, very interesting. If it is basically an extension of heating effect, it can have any light can extract electrons from the surface. Okay, but that is not happening. Okay, there are a few more other stunning observations. Okay, so first of all, if the frequency is important, not the intensity. If the frequency of the incident light is less than a certain minimum value, okay, then no electrons is getting emitted. And if the minimum frequency depends on the nature of the material of the emitter plate. So for example, if you are using zinc, or if you are using some other material, say iron, based on what material you are using, okay, the frequency required will also vary. Okay, so it was found that certain metals like zinc, cadmium, magnesium, etc. responded only to ultraviolet light having short wavelength. Okay, so this is called photoelectric effect. So it was there are other material examples are also given. However, some alkali metals such as lithium, sodium, potassium, cesium and rubidium were sensitive to visible light as well. So these materials are visible to visible light. Some materials are visible to only ultraviolet light. So which is very, very interesting, right? And these electrons emitted by light are called photoelectrons. Photo means light. Okay, the term photo is definitely, we know that photo is we used to refer to the image that we take. Okay, the picture, right? So that is also a name for photo. Photo comes from the fact it is a light. Okay, so light emitted by light, that's why this is called photoelectrons, and the phenomenon is called photoelectric effect. At that point of time, no explanation was possible. Many people gave different types of explanation, but nothing was satisfactory. And this is the experimental setup. So they are showing some light over here. This is the source. This is a quartz window. So light is falling on metal surface and electrons are emitted, and there is a mechanism like this. So they are collecting the electrons on this side. Okay, that's how they know if the current is flowing, then they know electron is flowing. If the current is not flowing, they know there is no electron is flowing. Okay, so this is the experimental setup. If you want, you can read it. Not super experimental setup is not important. Effect of intensity of light on photons, photocurrent. There are different process. First is intensity of light, photoelectric current. Now if you are getting the light, suppose you are lighting a zinc using a ultraviolet ray, and if you are, instead of having one ultraviolet ray, you are using 2 ultraviolet ray or 5 ultraviolet ray, 10 ultraviolet ray, then what will happen? As you are increasing the intensity, the current also increases linearly. More intense is the light, more current you will get. So they are linearly proportional. If the intensity is 0, that means no light is lit, then you will get no current. So basically this is the straight line graph. Okay, very important. All the graphs in this chapter are super important. Okay, a lot of question comes from these graphs. Okay, effect of potential in photoelectric current. Okay, so what is happening when you applying different potentials? So as you can see that if you have a different intensity of light, I1, I2, I3, there are the 3 different potentials, and if you somehow try to stop the electrons coming out of the plate, okay, so basically you are applying reverse potential so that electrons cannot go to the other surface. So there is a negative potential at which electrons are not able to go to the other plate, so current becomes 0 at that certain potential. Now no matter whatever is the intensity of the light, the potential which is called stopping potential, the negative potential which is called the stopping potential, that stopping potential is basically same for whatever intensity of light you are using. Right, we have seen that structure. So there was a plate where light is falling, so electron is coming. Electron is coming means it is being collected on the other side and it is being flowing through the circuit. Now if you apply a potential so that this plate itself is positive, the plate through which the current is emitting, electrons are emitting, they are positive. So that means the electrons, instead of leaving it, it will immediately after it leaving, it will try to come back to the positive plate. But there is also electrons, they have some energy, so they might still go to the other plate and you will still get some current. But if after certain value of this potential the current becomes 0 in that circuit, then that voltage is called stopping potential. This is very important concept. Okay, we will see that in Einstein's equation how this is related. But current, the maximum current, this is called saturation current. Okay, so current becomes constant. The maximum saturation current is basically dependent on the intensity of the light, right? No matter how much voltage you put in the forward direction, after some time current becomes constant. Okay, so this depends on the intensity of the light, maximum saturation current. But the stopping potential is independent of the intensity. It depends only on the frequency of light. For different frequencies you will get different stopping potential, but for same frequency, different intensity, you will get same stopping potential. Let's see the next graph. So here we have different frequencies are used of same intensity. Intensity of the light is same, but frequency of the lights are different. As you can see, higher the frequency, higher is the stopping potential, means more negative stopping potential is needed. So here nu 1 is the smallest frequency, and you can see that in this case nu 1 is nu 01. Now as you are increasing the frequency, higher the frequency, more stopping potential is required to stop the electron. Okay, so this is very interesting. So stopping potential depends on the frequency and not on the intensity. These are all the things that was not able to explain. Now stopping potential and frequency of incident radiation, they also changes linearly. This is the graph. Metal A, metal B, they have shown for different metals how the stopping potential varies with the frequency of incident radiation. This is only frequency. Okay, this is only frequency, whereas this is the stopping potential. So as you are seeing that there is a minimum value of frequency required to get the light, otherwise you should have get it from the 0, but you are not getting it from the 0. The minimum value is called the threshold frequency. Okay, so the stopping potential V0 varies linearly with the frequency of incident radiation for a given photosensitive material. There exists a certain minimum cutoff frequency nu 0 for which the stopping potential is 0. Okay, the maximum kinetic energy of the photoelectrons varies linearly with the frequency of incident radiation, but it is independent of its intensity. For a frequency nu of the incident radiation, the lower the cutoff frequency nu naught, no photoelectric emission is possible, even if it is the intensity is very large. So these are the very few things. Now these are the summary of the entire experiment that we have done, and this is the Hallwach-Leonard observation. If they ask you what is the Hallwach-Leonard observation, then you have to mention 3 points from this highlighted portion. So these are the portion where you have to write it for Hallwach-Leonard experimentation. What is the Hallwach-Leonard explanation observation? These are the observation made by Hallwach and Leonard. So Hallwach and Leonard, let's see. For a given photosensitive material and frequency of incident radiation above threshold frequency, the photoelectric current is directly proportional to the intensity of the incident light. So current is directly proportional to intensity of light. For a given photosensitive material and frequency of incident radiation, the saturation current is found to be proportional to the intensity of radiation. Again, saturation current depends on intensity. Current is very important. Current depends on intensity. Okay, whereas the stopping potential is independent of the intensity. So stopping potential is independent of intensity. No matter how intense the light, stopping potential is same for whatever light you will use. Only the saturation current depends on the intensity. For a given photosensitive material, there exists a certain minimum cutoff frequency for which the incident radiation, called the threshold frequency, below which no emission of photoelectron takes place, no matter how intense the incident light is. Above the threshold frequency, the stopping potential, or equivalent to the maximum kinetic energy of the emitted photoelectrons, increases linearly with the frequency of the incident radiation, but it is independent of its intensity. So threshold frequency is very important in case of photoelectric effect, right? So as the intensity is increasing, the energy of the emitted photoelectrons is increasing, but the current is saturated current. Saturation current depends only on the intensity, whereas stopping potential or the maximum kinetic energy depends only on the frequency. Very important. The photoelectric emission is an instantaneous process without any apparent time lag, even when the incident radiation is made exceedingly dim. Very interesting. So if it was the extension of thermoionic emission, then you have to light up the metal for some time, say 1 minute, 2 minutes, 5 minutes, so that the metal can absorb the heat, then the electron will come out. Okay, but instead of that, this process is almost instantaneous. Instantaneously means whatever light is coming, the electron is absorbing the energy and coming out of the metal. So this is very instantaneous process, which cancelled all the known theories at that point of time. So it was very difficult for people to explain it until Einstein came. Einstein is obviously the pioneer, so he is the modern father of physics. So he came up with the equation, that is the kinetic energy coming of the electron is basically h nu minus phi naught. He said that all the light that is coming have a fixed amount of energy, and he called it quanta. Okay, and the quanta means a packet of energy. I have explained briefly about quanta during my electric charges and field chapter in my KCET series. You can check that out. Okay, so quanta is basically a packet of energy which has a fixed value, and it depends on the frequency of the radiation. Okay, it depends on the frequency of radiation, and one quanta of light have an energy of h nu. So this is the one quanta of light. The phi naught is the work function. Okay, it is called work function. Basically this is the minimum amount of energy required to release the electron. So this is the energy with which it is bound to the metal surface. So if you give more than that energy, then only the electron will come out of the surface, and whatever energy that with which the electron is coming out, that is the Kmax, maximum kinetic energy. This is the photoelectric, this is called as Einstein's photoelectric equation. Very important. Okay, you have to write it down. Sometimes they will ask you write and explain the terms. Sometimes they might ask you what is the Einstein's photoelectric emission, problems might come from here. So this is a very interesting and important part. You have to read through this entire portion one by one. This part is compulsory reading. Now EV naught is equal to h nu minus phi naught. These are the formulas, or V naught is the stopping potential. Basically stopping potential can be calculated using this formula, h by E into nu, phi naught by E. And also one more formula, I think, which is not given here, or maybe I missed that. So there is one more formula which is basically giving phi naught. So phi naught can also be written as h nu naught. This nu naught is the threshold frequency. This is another way. So we sometimes write it that K max equals to h nu minus nu naught. Okay, so this is another form. Okay, and K max is E into V naught. Okay, so these are the things. This V naught is stopping potential, E is the charge of an electron. You can use it to calculate the V naught. So these are the forms that you have to remember. Okay. Now Planck's constant is 6.626 into 10 to the power minus 34, or 6.6 into 10 to the power minus 34. Okay, so whatever value, this is generally given in most of the cases. Now particle nature of light, the photon, so they have given the explanation of the photons. So this is the explanation of Einstein. You have to understand this explanation. The interaction of radiation with matter, radiation behaves as if it is made up of particles called photons. So these are the explanation of Einstein. So if they ask you explain photoelectric write for Einstein's photoelectric emission and explain it, these are the explanations that you have to remember. Each photon has an energy E equals to h nu, and momentum P is equal to h nu by c, and speed c, the speed of light. So all photons are basically moving with the same speed of light. They are assuming it's a space of vacuum, or obviously in air. Okay, in any other medium the speed will change, but they are assuming that it is in experiment is done in vacuum. So all the speed of the wave is basically c, that is the speed of light. All photons of light of particular frequency nu or wavelength lambda have the same energy E and the momentum P. So all photons of a particular light, they have same energy and same momentum, which is very interesting. The light of different waves have different frequency, have different energy and different momentum, right? Now this is independent of the intensity of the light. So whatever the intensity of the light may be, by increasing the intensity of the light given wavelength, there is only an increase in the number of photons. So when you are increasing the intensity, suppose at intensity 1 only one photon is coming. Now at intensity 100, now what you have done, you have increased the number of photons, that is 100 photons, but each photon will have the same energy as the one photon. So that is very interesting. Photons are electrically neutral and are not deflected by electric and magnetic field. So photons are unlike electrons, they are electrically neutral like neutrons. So they do not get attracted or repelled by any electric field, electric or magnetic field. In a photon particle collision, such as photon electron collision, the total energy and total momentum are conserved. That is very interesting. There is a theory based on entire of this thing, Compton scattering, but that is not there in this syllabus, so I am not going to discuss. You just need to remember it. Now wave nature of matter, this is another interesting part. So there was a history student called Louis Victor de Broglie. Okay, this is not Louis Victor de Broglie. So he was studying history, okay, that point of time, and then during that point of time, okay, Einstein gave his famous theory of photoelectric emission, and then he thought, okay, so what Einstein is saying, that light, which is a wave, it is behaving like a particle or photons. Okay, so he thought that nature is very symmetrical. Okay, so if a wave such as light can behave as a particle of photon, then small particles such as electron, they can also behave like a wave. So his analogy was, so starting point of this theory was, nature is very, very symmetrical. If wave is behaving like particle, particle should also behave like wave. So that's what is starting point, and then he formulated his famous de Broglie equation, and from here the journey of quantum mechanics started. This is the starting point of the quantum mechanics. That's why I said when Einstein gave his theory, based on that theory quantum mechanics developed. So this is how the quantum mechanics started. Quantum mechanics is when we start dealing with very, very small particles at the quantum level. You may have seen the movie Quantum Mania, that Ant-Man and Wasp, Quantum Mania, right? You have seen that. So this is basically they are talking about quantum realm, etc. Quantum realm means very, very small. Okay, so that's why the Ant-Man has become very small and smaller than a normal particle to go into the quantum realm. Okay, so that is a physics. Physics is very weird there. Okay, that is a very interesting movie. If you have not watched it, you can go and check it. Anyway, so what is happening is that so basically he said that if particle moves with a very high speed, then it will have a wave like nature. So what he said, the momentum of that wave is given by hc by nu. Now from there he calculated the wavelength of the particle. Okay, so particle, for an electron which is moving very fast, okay, it behaves like an wave, and that wavelength is given by lambda, that is basically h by p. Okay, in terms of wavelength you can calculate the nu also, but in case of wave, the difference is, what is the difference? In case of wave, okay, the wave is already moving with the speed of light c. In case of particle cannot attain the speed of light c, so it is moving slightly less than speed of c. That is the major difference. That's why instead of using c, we generally use p for momentum. We represent momentum. Momentum is more prominent for particles, and here you have we can calculate the wavelength for some particles. For example, I think they are trying to calculate the speed of a mass, say 0.1 kg, say for example a ball, okay, of 0.12 kg and moving with the speed of 20 meter per second. So it is basically normal ball or normal say car which is traveling at say 10 meter per second or 100 meter per second, whatever it is. Okay, so if you calculate their wavelength, for example, if I am moving in the room, okay, I have some speed, say 1 meter per second, and my mass is say 70 kilograms. So you can calculate my wavelength as well, but the wavelength will be very, 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 very small. So very small wavelength means you cannot detect that small wavelength. You have no such devices to find that small wavelength, and in fact all the materials around me is very, very bigger than my wavelength, so I cannot pass through that object as well. So there was some science fiction, I become a wave, I can travel through matter, I can travel through objects, which is actually absurd because the wavelength that you might have is very, very small. So to observe wave nature of matter, what is the required is the mass has to be very, very small and speed has to be very, very high. Then only you can see the wave nature, and it is happening. It is very, very true for all the electrons orbiting around the nucleus. Okay, you have heard about electron cloud, etc. Basically they are actually in a wave-like form inside the nucleus. Similarly, in case of a large hadron collider, where they have done a lot of experiment, you may have heard about it. So electrons are getting accelerated at a high speed, so they are also behaving like waves at that point of time. So there are a lot of examples where they are actually behaving like wave, and because it is the starting point of quantum mechanics, this chapter is very, very important. This is the common formula for all the formulas for Einstein's wave equation. Here it is, they have mentioned it is half mv max square. V max is the maximum speed, okay, V max is a maximum speed, V naught is the stopping potential, okay, E is the charge of electrons. So half mv max square is equals to E V naught equals to h nu minus phi naught equals to h nu minus nu naught. Okay, so this is the formula that you can remember. This one formula will give you access to all the other formulas. Okay, there are a few dimensions you can check. Okay, Planck's constant is joule second is the unit, and this is the dimension. This is the dimension you have to remember. Sometimes they might ask question based on that. Stopping potential is basically voltage, work function is basically energy, threshold frequency is frequency, and de Broglie wavelength is length. So these are the formulas that you have to remember from this chapter as well. So with this we have concluded this chapter, and if you have any questions, any doubt, don't forget to mention this in the comment. And if you are watching our channel for the first time, don't forget to subscribe and give it a thumbs up. I'll be back with more chapter very soon.